Good morning to all of you. I welcomes to all in our lecture series on solid state physics. Today we are going to discuss about Debye's model of lattice heat capacity. In this lecture I am going to explain about this model directly from the book, and I will be tell to you that what is the portion that you have to write down the note for your exam purposes. Okay. So before we have to start about this model, first we have to recall that why this model has been developed, because previously we have been discussed about Einstein model and classical theory model of specific heat capacity. Why these two models has been failure and why this model has been developed. With a short revision we are going to be discuss. See, in case of classical theory, they have been considered that the vibration of the lattice points, suppose this is a crystal, and these are the lattice points, these are your lattice points, and at the lattice point suppose this is your atom. So according to classical theory, they have been assumed, that means Dulong-Peters has been given this theory. According to them, one atom is oscillate along x-axis, can be oscillate along y-axis, can be oscillate along z-axis. That means one atom acts as a three-dimensional oscillator. Okay. Or we can say one atom will be considered as three 1D oscillators. And total energy of this atom has been considered as, suppose we have to consider the along x-axis, this will be x square by 2m plus half m omega square x square. Here, in case of classical theory, it has been considered that all the energy values is going to be acceptable as per the classical theory, but it is again modified. So if we have to assume these things, then what we found? We found the specific heat is a constant value. What is the constant value? That is equal to 3R. That means around molar specific heat we found around 6. I can show you here. Here you can just check your note that we found that Cv equal to 3n kb. If we are going to consider molar specific heat, Cvm will be equal to how much? 3R will be approximately a constant value, that is 6, approximately 6 value. So if we are going to be analyze the behavior of the specific heat of different substance with temperature above 300 Kelvin, it touches the value 6, but below 300 they have been not the value given the value 6. That means below 300 it decreases, means from the low temperature to 300 degrees 300 Kelvin, the specific heat of the substance silicon, germanium, silver, these are the three examples. We can found that this specific heat increases like this. So this increase of specific heat with increase of temperature at the low temperature, it could not be explainable by the classical theory. It is again modified by the Einstein. Detailed video it is there. I suggest that you have to go through that. So according to Einstein, he just modified that each and every lattice site will be considered as 3D oscillator. Same assumption, or we can say one 3D oscillator is equivalent to 3 1D oscillator, but according to Einstein, he accepted the energy is not to be continuous. The energy of the each harmonic oscillator is not continuous, it is discrete. Because in quantum mechanics we have been already studied that En equal to n plus 1 by 2 h cross omega, means here n is equal to 0 1 2 3, means energy of the oscillator, one oscillator, is not going to be continuous, it is discrete. So Einstein assumed the quantum harmonic oscillator instead of classical harmonic oscillator. So if it is so, then the energy of the harmonic oscillator is not going to be continuous, it will be discrete. Okay. Due to this assumption, the model has been explained the increasing of specific heat at low temperature, but not perfectly. So this is the last expression of specific heat. Actually, in case of Einstein specific heat detail, I have been discussed, you can go through that. I can recall you that at high temperature behavior for Einstein theory, it well matched with the classical, is equivalent to 3R at high temperature. Low temperature, the value came as this much. Okay. So here you can see e to the power minus theta e by t, one factor it has been found, and if we have going to consider along this side t by theta e, then along x axis we have been considered t by theta e, and this side we have been considered the specific heat. So here you can see that one factor it is e to the power e to the minus theta e by t. Okay, or we can write e to the power 1 by t minus theta e. Okay, so if t by theta e is going to be increased, this whole is going to be decrease. If whole is going to be decrease, then e to the power minus, suppose I am going to consider this is x. So if x is going to be decrease, this e to the power minus x whole is going to be decrease. Sorry, it is going to be increase, because this is nothing but 1 by e to the x. Okay, if this e to this x is going to be decrease, this whole is going to be increase. Okay, so here you can see that as t by theta e increases, this value also increases. That means Einstein also explained why it has to be increased, but the behavior of the CV at very low temperature not followed the exponential increasing. Here Einstein told that it has to be increased exponentially. With increase of temperature, with increase of t by theta e, it has to be increased. However, in the reality, CV increases following this law. That means the CV, the increase of CV with temperature is not exactly follow the Einstein prediction. So again it has been modified, the model whatever Einstein has been considered, that it is not going to be acceptable 100%ly. So that model again has been modified by Debye. Okay, so after modification, that model Debye approximately approached to the experimental result. So before we have to start Debye's model, first what is the assumption that I am going to be explain you have to just watch it. Okay. See, I told initial that today in this class or Debye model, whatever I am going to explain, that I am going to explain from the book directly, and you have to write the note what I am going to be say to you. Okay. Because you can say that this is your one type of writing of developing your writing skill of the note. Okay, only this chapter, only this topic. So here it was observed that in low temperature region, in the Einstein curve deviates from the experimental observed, whatever we discussed. In 1912, Debye pointed out that Einstein's assumption that the atoms of the crystal or the atomic oscillators vibrate independently at the same frequency is not justifiable, and suggested that oscillators are coupled each other, oscillating relative to their neighbors in the lattice, and are capable of producing spectrum of frequency. Thus the essential spectrum of frequency, or you can say spectrum of waves. Okay. Thus I am just going to be increase somewhat zoom. Thus the essential difference between Debye model and Einstein model is Debye considered the vibrational mode of the crystal as whole, whereas Einstein considered the vibration of single atom with assumption that atomic vibrations are independent of each other. As the atoms of the crystal no longer vibrate independently, it is convenient to work with vibrational modes of a system. This is important. Vibrational mode of the system rather than the vibrational mode of the single atom. So I suggest that you all have to be write this much. You all have to write. These are the assumptions and the development of the model by Debye by comparing with Einstein. So you just write this much. All the lines you write, it will be better. If it will be in your note, it will be better. So I am going to explain what it is. See, what Einstein told. Einstein has been explained that suppose this is a crystal. Already I told this is a crystal, and these are the lattice points. These are the lattice points. Each lattice points, or the atoms at each lattice side, they are vibrating independently with each other. There is no connectivity between this atom and this atom, and the vibration of this atom and this atom independent with each other, but same frequency. But here Einstein has been assumed that the energy is discrete. Okay. But Debye, he just modified this model that this atom, that means all the lattice sides, they are coupled with each other. You just imagine that we have been studied our one dimensional lattice vibration, monoatomic lattice vibration. At that time we have been considered that all the atoms or all the lattice sides has been connected with each other with a massless spring. So this type of model has been considered by the Debye. That means all atoms in three-dimensional lattice, all the atoms or all the lattice sides, they are coupled with each other. They are connected with each other. And the whole atom is going to be oscillate with a particular frequency. Okay. Here Einstein considered that all the atoms are independent with each other. There is no connectivity between one atom to one atom, and oscillates with the one particular frequency, suppose omega. But here Debye modified this model and told that all the lattice sides or the corresponding atoms at the lattice side, they are coupled with each other, connected with each other, and going to be vibrate with a frequency. That means whole system or whole crystal is going to be vibrate with a frequency. That frequency can be vary. That frequency can be vary. That here last sentence of this book, in here it is written that as the atoms of the crystal no longer vibrate independently, if we are going to consider that they are coupled with each other, they are not independent with each other. If it is so, it is convenient to work with the vibrational modes of the system rather than vibrational mode of a single atom. So here vibrational mode means belongs to one frequency, belongs to another frequency. Suppose with 4 frequency one atom can vibrate, we can say that the 4 different vibrational modes. Here, instead of considering one single atom having different vibrational modes, the Debye has been considered that the whole system is going to be vibrate with a different frequency or the so called vibrational mode. That means here the whole system, two-dimensionally I can show you that this is the two-dimensional lattice, how they are coupled with each other. The whole system is going to be vibrate with a particular frequency. That frequency can be vary, or that will be called as the different modes. So if the frequency is denoted by mu, then we can say that the different modes means mu n. It can be mu 1, it can be mu 2, it can be mu 3, means different frequency. With different frequency, the whole lattice which are coupled with each other, they can vibrate with each other. So this is the developed model has been considered by the Debye. So now before we have to discuss about Debye's model in detail, first it is need to find out the number of modes in a particular frequency range. Number of modes in a frequency range. So today we are going to discuss this one. What will be the number of modes or number of frequency can be possible in a particular frequency range if we are going to consider a crystal, okay, or the so called system. So for this you put a heading, that is vibrational mode of continuous medium. So here this is when they are coupled with each other, it is looks like a continuous medium. So for that you just put a heading that vibrational modes of a continuous medium. Okay. So here I am considering I am following 2 books. About that book I am going to give the information in the description. You can find from the description about these 2 books. Solid State Physics Gupta Kumar, and one is Puri Babar. You just put this heading. See, here I am suggesting you that try to just develop your skill how you can write the note from the different books. This is the my motivation, that I believe that you can write by oneself. Okay, I will be explain all the things from the book, and also I will be say that which portion you have to write and which portion is not required for the exam purposes. Okay, so here this is your heading, whatever I told, vibrational mode of a continuous medium. Now, in order to consider the vibrational modes of continuous medium, because I told that if we can found the different vibrational modes in the system, then we can easily find out its a specific heat, because specific heat is directly depends upon the vibrational properties of the system. So as in your classical and Einstein theory, these lattice sides has been considered as independent, but it is coupled here. In case of Debye, it has been considered as coupled with each other. Okay. So for that, to finding this one, first we have to consider one dimensional, then we have to consider the three dimensional picture. Let us first consider the simple case one dimensional continuous string of length L fixed at the two ends as shown in the figure 3. So here this is the figure that suppose one string has been fixed in between the two side and two end as shown. In this case, stationary waves are set off with specific wavelength such as n lambda by 2 equal to L. Suppose the length of this wire, or we consider one dimensional string, so string of length of this string is L. Okay. So what are the possible wavelength can be possible when the string is going to be vibrate? You see, this is the first one, means half wavelength, and this is the second one, that means second wavelength, and like that. So here you can see for this type of vibration, for this one, for this type of vibration, length is how much? Length always is L. Here the length of the string is L, but this is half of a wavelength, right? So I can write, we can write that lambda by 2 is equal to L for the first case. Okay. For the second case, n equal to 2, lambda equal to L. See here, this is the full lambda or one wavelength in the L, in the length L. So I can write 1 lambda in the length L, or lambda equal to L, right? In general, I can write what? N lambda by 2 equal to L. See, for n equal to 1, this is satisfied, L, lambda by 2 equal to L. This is L equal to n equal to 2, it will be lambda equal to L. So n equal to 3, it will be equal to L. That means 3 lambda by 2 equal to L. That means another wave can be possible like this. The second mode, this I can say this is one mode of vibration, means with one frequency or one wavelength. This is another mode of vibration, means another frequency or another wavelength. Next mode will be like this. Will be like this. No need to write, draw in your note. Only two you have to draw in your note. So here you can see that this much length is L. L is equivalent to 3 lambda by 2. Okay. This is 1 lambda by 2. This is another. See, this length is 1 lambda by 2, 2 lambda by 2, 3 lambda by 2. So here, for next frequency or next mode, it is 3 lambda by 2, but length is L. Okay. Likewise, in general, I can write, or we can write, n lambda by 2 equal to L. Okay. So here, different possible wavelength or different possible frequency in between 0 to L when the string is vibrating, that is nothing but called as the vibrational modes. Okay, so vibrational modes is nothing but the different frequency with which the string can vibrate. See, whatever I am explaining the extra things, you can write in your note. But for the exam purposes, how much I am telling, you have to just write those things for the exam purposes. So here, in this case, stationary waves are set off with the specific wavelength, so that in general we can write this one. It should be remembered that if only one end is fixed, then any wavelength can be propagated. So this line is not required for the example, for the examination point of view. What this line is, this line not required for the examination point of view, but what is it? It is explaining. See, if there is one free end, one is fixed, another is free end, then any type of wave can be possible. But as these are fixed, only some discrete lambda value is going to be possible. That discrete lambda value is this much, the so called mode of vibrations. So I told that this line not required for your exam. So you can remove this line from your note. Now at a particular time, at a particular point, what will be the displacement when it is vibrating? See, it is x equal to 0, this is x is equal to 8. At particular x, suppose at this point, at a particular time, for a particular frequency, what is the displacement? What is the displacement from its mean position to up or down? What will be the displacement? That is nothing but is uxt. Okay, represent the displacement of the string at x at time t, and the wave equation is given by here wave function. It has been written mistakenly, so you just write the wave equation. The wave equation means whatever the wave is propagating through this length, the general equation is del square u by del x square is equal to 1 by c square del square u by del t square. This wave equation already we have been studied in our second semester, so no need to derive here. That means if a wave is propagating, the differential equation is nothing but in this style. You studied, just recall that d square y by dx square is equal to 1 by v square d square y by dt square. In this format you have already studied. So here the wave, whatever we are considering, that is inducing inside this length with a different frequencies. So in general we can write the wave, this is equation, the wave equation or the differential form of wave equation. You can write the differential form. If you write, it will be better. The differential form of wave equation is given by this one. Let this is equation number 1. Okay, here Cs is the velocity of wave propagation. The solution of this equation number 1 already we have been studied at that time, will be in this format, will be a sin n pi x by l cos 2 pi, this is mu n into t. Let it is equation number 2. Here n always has to be positive integer, because here n, you can see n I can take 1, 2, 3, not to be considered -1, -2 like that. So here n is always positive. Okay, for this n we have to consider only the positive values for this discussion. The wavelength and frequencies are given by, what are the wavelength and frequency we can get? Here you can see here n lambda by 2 equal to L. So for from this equation we can write lambda n equal to 2L by n, right? For a particular value of n, the so called lambda n will be this much, and mu n equal to Cs by lambda n will be equal to this much. You got my point? See, we know that V is equal to S by T. Okay, here S by time period equal to S is lambda, time period is equal to T, or we can write lambda into mu. Okay, or mu will be written as V by lambda, or V if it is written as Cs, so it will be Cs by lambda n. Okay, so it will be Cs lambda n is written by 2L by n, so it will be n by 2L. Lambda will be 2L by n, so it will be n by 2L. So it is written as mu n equal to this one. So the wavelengths and frequencies, from this we can write this and this. So for value of n equal to 1, 2, 3 like that, the frequencies are this one and this one, and corresponding wavelength here you can write the corresponding wavelengths. Lambda 1 is equal to how much? For n equal to L, for n is equal to 1 it will be 2L, for lambda 2 it will be equal to L, lambda 3 equal to 2 by 3L dot 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 dot. So these extra things you have to write over here. Here it is written that the mu n, in general the frequencies are Cs n by 2L, and for 1 equal to mu 1 equal to Cs by 2L, mu 2 to Cs by 2L like this, and corresponding here you have just started the corresponding wavelengths are this, this and this. Okay, but this is mu n is considered as equation number 3. Okay, now I am erasing these things because some other things I have to explain, otherwise it will be overwrite. So here we found the spectrum of wave frequencies. See, the frequency, the first frequency is possible is this one, the second one is this one, third one will be this one, like that. Fourth one will be 4 Cs by 2L, fifth one will be 5. That means either this frequency will be possible or this frequency will be possible. In between that, if we are going to consider 1 point, see, mu 1 is equal to Cs by 2L. This is the first frequency will be possible whenever it is vibrating. The first frequency will be this one. The second frequency will be this one. It is constrained that it has to be come out this one, 2 Cs by 2L. Suppose you are going to say that is it possible 1.5 Cs by 2L? No, it is not possible. It is not possible. So hence we can say that the discrete spectrums of a frequency we found. Frequency spectrum is discrete. That is, only for that it is written. So this language you have to write, no problem. Now the number of possible modes of vibration in the frequency d mu will be how much? See, here we can see for n is equal to 1 frequency, 2 second frequency, 3 third frequency. So we can found here, you can just see that mu n is equal to this equation, Cs by lambda n or Cs n by 2L, or n it can be written as 2L by Cs into mu n, right? Okay, 2n by Cs, no, 2n by Cs into mu n, right? So for 1, n equal to 1 first frequency, n equal to 2 second frequency we can get. That means if n equal to 1, we can get this number of frequency. So this is nothing but your number of mode of vibration corresponding the frequency mu n. So if we want to find out the number of modes of vibration in the frequency interval del mu n will be how much? Just use the do the derivative this side, we can get it. See what we can get. We have n equal to 2L by Cs into mu n, right? Now dn will be 2L by Cs into d mu n. So this is the number of modes of possible modes of vibration in the frequency d mu n in the small interval, or no need to write n, because we are considering the interval. This is the interval. So dn is the number of modes of vibration in the interval, frequency interval, this one. Okay, this one. So let this equation number is 4. Okay, now whatever we discussed, if I am going to consider those discussion in 3-dimensional, because for our convenient we discussed 1-dimensional string, and it is vibrating, the possible frequencies or wavelength when it is vibrating, blah blah. These are the things we have been discussed. But reality is that reality is this one, not 1-dimensional vibration. 3-dimensionally they are coupled, they are vibrating like that. So 3-dimensionally vibration means we have to consider the 3-dimensional wave equation, right? So like only for that, expanding the above case, whatever we discussed 1-dimensional, if we are going to expand in case of 3-dimension, the wave equation will be written as, this is the 1-dimensional, d square u by dx square, right hand side is this one. In 3-dimensional, along x axis vibration, along y axis, along z axis we have to consider. So d square u by dx square, d square u by dy square plus d square u by dz square equal to 1 by ca square into d square v by dt square. Let this equation number is 5. And the solution of this equation number 5, see, if the solution of this is this one, then the solution of this one will be a into sin nx pi x by l, sin ny pi y by l, sin nz pi z by l into cos 2 pi mu into t. Let this equation number is 6. And here nx, so we have to remember one thing, nx, ny, nz are always positive integers, Now if we are going to be substitute this 6 in equation number 5, we are going to get this much. You can try this in your rough you can try. I am going to just give one hint, you can identify. See, here it is telling that you are going to substitute this much for in this equation number 5. That means first we have to consider del square u by del x square. Del square u by del x square means here what is the which one is the function of x? This one is the function of x, right? This one is the function of x. So if I am going to take the double derivative, it will be how much? Nx square pi square by l square. See, pi square l square taken outside, so nx square pi square l square, and sine for the first derivative, sine will be cos and cos will be sine. Okay, and likewise if we are going to consider d square u by dx square, so it will be n y square pi square by l square, again minus same thing. For this one, if we are going to consider this one, this is going to be derivative, so this will be plus, again plus n square n z square pi square by l square and sine minus sine nz pi z by l. You do it in your rough, you can get, and right hand side it is that there d square u by dt square. So d square u by dt square means the function of t is here. So this double derivative means 4 pi square mu square by cs. Already cs square is here, by cs square. So you can found that left hand side all the term will be same with the right hand side. The terms is going to be cancelled out. This sine terms, cosine terms will be cancelled out, and we are going to get only the coefficient value. Will be this much. You just try it. You just do it in your rough. No need to write in the note, because these are the simple derivative as we are going to consider you are the 5th semester B.sc students. So these derivatives only you have to do in a rough, and directly you have to write this one. So substituting value of 6, this means this solution, whenever we are going to be substitute 5, we can get this one. You just simply, this left hand side double derivative, right hand side double derivative. Here you just consider this equation, you put, you can found this one, pi square L square n x square plus n y square plus n z square equal to 4 pi square mu square c square. Okay, or it will be written as n x square plus n y square. These are the subscript. Okay, n y square plus n z square is equal to r square is equal to 4. You can see pi square got cancelled, so 4 L square mu square by c square. Let it is r square. Let it is r square. First you write this one, then you write this one. Okay, n x square, n y square, n z square is equal to this one, is equal to r square. Say, let's consider equation number 7. Okay. That means this equation is looks like say sphere, is looks like a sphere, right? Because what is the sphere equation? X square plus y square plus z square equal to r square. This is the sphere equation. So this is looks like a sphere. So we can consider the sphere. This is the sphere by considering nx, ny, nz. Nx, ny, nz. We can consider the so-called sphere. Corresponding sphere by can be drawn by considering nx, ny, nz. Okay. So now here it is written that so in 3 dimension case, the wavelength and frequency. Now wavelength and frequency is determined by the 3 integers nx, ny, and nz. So now from this equation we can found the frequencies and wavelengths, because here you can see that it is 4 L square mu square by c square, means as this is function of mu and velocity, obviously we can found frequencies and wavelengths from this equation. But these are the integers, these are the integers, all are the positive integers. Okay, so the possible positive integers will be called as the density of states or density of vibrational modes. Sorry, density of vibrational modes. Carefully you just watch it. Now we have to discuss about density of vibrational mode. You just put the heading of this one, density of vibrational mode. So here first our assumption, not our assumption but our consideration is that these 3 should have to be positive. Okay, and this is a nothing but a sphere equation, that is like this, x z square equal to r square. So in case of sphere, x component, y component, z component has to be positive, has to be positive. So when it will be possible, I am going to show you. See, suppose this is the sphere. Okay, this is the sphere and here is the this is your one axis, this is another axis, this is another axis, right? You can see that the, see, I am going to show you. See, this is your, okay, center will be here only. Okay, you just see from the center, this is one portion, another portion, back side one portion, here and one portion, here and another portion. At the bottom also 4 portions we can get. Okay, so you just imagine that all the x, y, z has to be positive. That means here we have how many parts? 1, 2, 3, 4 on the up, on the down also 4. That means we have total 8 parts, right? We have total 8 parts in the sphere. Okay, in the first quadrant, if we are going to consider the two dimensional first, second, third, fourth. But in case of 3 dimensional, here first quadrant, in the first quadrant this front side will be one and back side will be another one. Front side, back side, upper surface, below also 4. Though 8 parts we can found of a sphere. Okay, So which part, you just consider which part has all the xyz is positive. Only this part, only this part, only this part, which is 8th part of the sphere. Suppose this sphere volume is V, in V by 8, or you can say 1 by 8th of V contains all the positive x, y, z components. Likewise, as we are considering this nx, ny, nz all are positive, that means these all the values, whatever we are going to be consider, these all the values lie in this quadrant, or this in the not quadrant, in this octant. In 2-dimensional 4 quadrant, in 3-dimensional 8 octant are there, 8 octants. So in the first octant we can get all the nx, ny, nz's are positive. So hence, instead of considering whole sphere, this is a sphere equation having the radius is this one, considering whole sphere we have to consider 1 by 8th of that sphere. If this is the volume of the sphere V, we have to consider 1 by 8th of the volume of that sphere, in which nx, ny, nz all are positive. Okay. Now what are the possible values of nx, ny, nz in this octant will be nothing but called as all possible modes of vibration. So all the possible nx, ny, nz is called as all modes of vibration, all modes of vibration. Okay, but all modes of vibration means all frequency is going to be considered, but density of vibrational mode is nothing but number of possible, here it is written, the number of possible modes of vibration in the frequency range mu and mu plus d mu. So in this frequency range, in a small frequency range, what is the number of modes of vibration? That is called as the density of vibrational mode. So here we found the total number of modes of vibration in the volume for this case is this much. Now you can say that, sir, this is the volume, how it will be the number? Yes, this is the so called number, because why I am telling, the each point of this volume, each point, suppose we are considering this volume only, we are not considering the whole sphere, we are considering the sphere having the volume is this much, because in this volume nx, ny, nz is positive. Now I am going to draw that half portion only, that portion. In this sphere, whatever the possible nx, ny, nz, all the values, nx, ny, nz, all the values is nothing but called as the possible number of modes. Okay, so here each and every point is considered in this quadrant is considered as number of modes of vibration. You got my point? So in this octant, each and every point can be considered as mode of possible mode of vibration, because see, these are the explanation not given in the book, so you just watch it. So in this octant, in this first octant, as nx, ny, nz are positive and we are considering only the first octant, we are not considering back octant, we are not considering this side and this side, we are considering only the first one. In this octant, all the points, any point, I am going to consider any point and I am going to consider that will be the possible mode of vibration. But density of vibrational mode is nothing but number of possible mode of vibration present in the frequency range mu plus d mu, or in the range of radius r to r plus dr. Okay, so as these are the points, any point will be considered as the possible mode of vibration. So here its total volume is how much? V by 8. Okay, its total volume is nothing but called as the number of, carefully you have to listen, this is logically how it I am correlating, you just, this volume is represents the number of possible mode of vibration. Now you can say that, sir, how the volume is going to be number of modes of vibration? Because here each and every point having the unit volume, and both all are equal. This is the unit volume, this is the unit volume, this is the unit volume. This point is considered as the unit volume. So whenever I am going to add all the points, what is the volume I am going to get? I am going to get this volume. Okay, so this volume is nothing but number of possible sum of the or total number of possible mode of vibration. Suppose I am going to consider in this volume 100 possible mode of vibrations, or 100 points. These are the 100 points is possible. That means its volume is 100 unit, because each and every points as considered as one unit of the volume. If I am going to consider all the volume, that means I am adding all the volume of this point, that is 100, whatever I given the example, right? Now as we are considering the density of vibrational mode, which has to be considered in between radius r to dr, so only for that we are not going to consider all the volume of this part. We have to consider the volume which is in between. Suppose this is the radius r. We are not going to consider whole volume. We are going to consider the number of points will be possible in between r and r plus dr. That means in this small volume, whatever the number of points, that will be called as your density of vibrational mode. Got my point? So this is only thing. So I suggest that whatever I am explaining, you have to write down in the rough, and you have to paste here. How you have to write, I am going to say you, wait. So this is nothing but your whole volume of this octant, and that volume is nothing but V by 8. This will be nothing but number of possible mode of vibrations. But if we are going to consider the number of modes of vibration in between r and r plus dr, that will be called as the so-called density of mode of vibration. Now that is nothing but z mu and d mu. What is the value? Now we are going to be calculate. Okay. See, here we found that r square is how much? R square is this much. Okay. The volume of the sphere having the radius r is equal to how much? 4 by 3 pi r cube, right? First take the derivative. So dv will be equal to 4 by 3 pi 3 r square dr, or dv will be equal to 4 pi r square dr. Okay, so now this volume is nothing but covering the volume in between the radius dr. That means in this volume, here this is I am representing in 2D, but you imagine that this is in 3D. Okay, so this volume is nothing but dv. Okay, this dv is nothing but this one. which is in between, this is R and R plus dr. So this element is nothing but called the dV. Okay, now what will be the value of this one? That what will the value of this dV will be nothing but called as the so called Z mu and d mu. You got my point? Because already we assume that each and every point is the unit volume, contains the unit volume. So whatever the volume of this element, that will be represent number of possible modes of vibration in this range or in this radius in between R and R plus dr, or you can say mu and mu plus d mu. Okay, so now what will the value of dV? See, dV will be equal to 4 pi in case of, sorry, here I done one mistake, simple mistake, that we have to consider the volume of 1/8, no, 1/8, because we are considering only octant, first octant, 1/8, this is 1/8, this is 1/8. So 1/8 of 4 pi, instead of r square we can write this one, instead of r square, here here it is written, you just watch it, here you see 4 pi, this is r square is nothing but 4l square mu square by ca square, okay, into 1/8 4 pi r square. Now what is the value of dr? What is the value of dr? That is somewhat interesting, because already we found that number of possible modes in the frequency interval d mu is equal to how much? This much, number of possible modes. So number of possible points, so corresponding number of possible points in the radius dr will be nothing but same thing, because here I am correlating radius to frequency. So instead of dr, what we can write? We can write dn. Okay, so here dv will be equal to 1/8 4 pi 4l square mu square by ca square into dr. Instead of dr we can write dn. Dn value is how much? 2l by cs into d mu, 2l by cs into d mu. Okay, so as I told that the so called volume element represents the number of possible mode of vibration. So instead of dv we can write dn equal to 1/8 this much, whatever written in this book. Okay, so this is the explanation in short given in the book, but I suggest to all of you that what I explained, you go through this video and you have to write these things. The whole volume we have to consider. We are not going to consider, carefully listen, we are not going to consider whole sphere. We have to consider only first octant, in which nx, ny, nz will be the positive. So for first octant means the volume will be v/8. Okay, so here v/8 will be number of possible modes of vibration, total number of possible modes of vibration, because each point in this volume, carefully listen, each point in this volume considered as the unit volume. So total number of possible mode of vibration will be represents the total volume, that is v/8, that is the volume of the first octant. Okay, now the density of vibrational mode, that is Z mu d mu, will be considered or will be calculated the points in between R to dr. You have to draw this figure, then this figure. In the radius R and dr, or in the volume dv. Okay, so this will be calculated by considering the number of points in between R and dr. Okay, now the volume V is considered as 1/8 of this one, dv will be this one, dv will be this much, or dv will be this much. That means this dv, here you just write in bracket, this dv represents the number of possible mode of vibration in between R to R plus dr, or in this volume. So this number of possible mode of vibration will be equivalent or equal to the number of points. This volume, you have to write that this volume is nothing but the number of points, total number of points in this volume. Okay, that total number of points is nothing but total number of possible mode of vibration in the frequency range mu and d mu. Okay, number of points, carefully you have to listen. Number of points in between R to R plus dr is nothing but number of possible mode of vibration in the frequency range mu and mu plus d mu. So here the number of points in this volume which is enclosed in the sphere having the radius R plus dr and R is equal to the number of possible mode of vibration in the frequency range mu and mu plus d mu, which will be equal to dv equal to this much, what I told. So dn will be this one. Okay, here you just write that dn will be equal to dv because each point is considered as unit volume. This much you have to write, and finally you can get the eighth number equation. So I suggest that after follows what I told, you have to write, and you found equation number 8. Okay, equation number 8, here you got equation number, here you got this one. This is your equation number 8, and what I explained here, equation number 8 you got. Then you just each point correspond to set of 3 integers. No need to write, whatever I told that way you have to write, and you found that you have to put all the values. So here dn equal to this much, or you can write z mu d mu equal to this much. dn is nothing but z mu into d mu. Okay, so at last we found that z mu d mu is equal to this much, equation number 9, which is represents the density of vibrational modes. That means possible mode of vibration in the frequency range mu and mu plus d mu. In this format you have to write. You just modify this writing as what I explained. Okay, so then you have to write, for each frequency there are two transverse modes correspond to the deflection perpendicular to the direction of motion, and one is longitudinal mode corresponding to the deflection along direction of propagation possible. So one transverse mode possible, one longitudinal mode also possible. So only for that z mu d mu further can be written as, z mu d mu 4 pi v taken outside, and mu square d mu taken this side. Then, and here this 1 by c square is written as 1 by CSQ, 2 by CTQ plus 1 by CLQ. Why? This Ct is belongs to your transverse wave, Cl velocity of transverse, velocity of longitudinal, and this is 2, it is written because 2 modes of vibration possible in case of transverse modes. For each frequency there are 2 transverse modes correspond to here you can write, for each frequency there are 2 transverse modes possible to the possible perpendicular to the direction of propagation. See, this is your transverse waves. Transverse waves means this is your propagation vector. This side it is propagating, so it is vibration along this side and along this side. One is this side, another is this side. But in case of longitudinal, this is only along this side. The direction of propagation in which side? That side only they are vibrating in case of longitudinal wave. But transverse, they have 2 different mode of vibration as compared with your propagation vector. So for each you have to write, for each these 3 lines not required to, these 2 lines, first 2 lines not required to write. For here you have to write, for each frequency there are 2 transverse modes perpendicular to the direction of propagation and 1 longitudinal mode, 2 transverse modes possible perpendicular direction of propagation and 1 longitudinal mode possible along the direction of propagation. Okay, that means for longitudinal only 1 direction of propagation is to be considered. For transverse 2 direction of vibration is going to be considered. So only for that, for transverse case it is written as 2 by Ctq plus 1 by Clq mu square d mu. So this is our final expression of density of vibrational mode. So here we have to stop, and by using this Z mu d mu we are going to discuss in detail about the Debye approximation. Okay, so thank you so much for watching this video. In which way I told you, just write your note, and if you can send me and I will check your note. Okay, thank you so much. Thank you.